Okay, good morning, everyone. For those who have questions, put them on chat while the rest join. Okay. Right. Okay, so yeah, I saw the questions. So before I start answering your question, let me a little bit recap what we did. So things will stay clear in our mind, and then I answer your question and finish this section to this chapter, this section today. All right, so what we saw yesterday, we saw a fact. Let me remind you the fact. And we saw two tests. So the first fact we saw is the following. If a series converge, so if a series converge, so it means etc. converges. So if we know that it converges, then what can we say about the term, the individual terms themselves? Questions? You guys hear me? Think. Yeah. So if a series converge, what can we say about the individual terms when k becomes large? Anybody?
They approach zero.
They approach zero. Then the limit as k goes to infinity of the ak equal to zero. So if the series converges, then those individual terms by themselves will become very, very small. Okay, that's the first fact we saw. Remember that the fact tells me that if I know that the series converge, then the limit is equal to zero. So let us say a question. Basically a question.
Does that say equal to infinity or zero?
Zero. Why zero? Why zero? I want to understand the idea, because if those terms don't become small, if those terms, let us say, become close to a 1, for example, what will happen to the sum? Can the sum be a finite number? So if those
No, it's just going to keep increasing.
Right, so those terms will eventually, we will be adding 1 to 1 to 1 to 1, because here it's a sum. So it will be adding large number to each other. Therefore, the sum will diverge. Is that clear?
Yes.
Very important. You have to know what's with the picture. So suppose I have a problem, and I ask you the following question. I tell you, let sigma ak be a series. Okay, it means an infinite sum. It means we're adding terms, and we keep adding them till we get somewhere. And you're given. So you're given. I'm telling you that the following, that the sum is equal to 3. So sigma an is equal to 3, or sigma ak. So my question to you is, what can you say about the limit of the partial sum? What can you say about the limit of the an? Question addressed to you.
Wouldn't the limit of the partial sum be 3?
Limit of the partial sum is 3. Is he correct? Put on chat, yes or no. Is he correct? Wake up, guys. If you don't want to talk, just put on chat. Is he correct? Is the limit of Sn equal to 3? Yes or no? Yes, yes, yes. It means the partial sums becomes close to 3. It means those terms, as we add them, they become close to 3. What about the An? Back to you. 0. Why? Because if I tell you the sum equal to 3, so this means basically I'm also telling you that the series converge. So if the sum equal to 3, the only way this can happen if those terms become very small. Otherwise, it's going to blow up. Otherwise, the sum will go to infinity. Because if it doesn't go to 0, the first few terms can add up to 3. But after that, if the term say big, we'll be adding a big to a big to a big to a big to a big, and then it's going to go to infinity. All right? So that's some of the fact from yesterday. Now, then the two other things that we saw were the following. We saw the divergence test, which is basically, which tell us the following. Remember what does the divergence test tells me? Who can say it in words? Let me pick somebody. Marek, you're with me, right?
Yes.
Yeah, tell me. What's the divergence test tell us?
If the limit of the series is k approaches infinity.
Limit of what? You have to be very precise.
If the limit of a series?
No.
No.
No. It's basically what we call the converse of that. If the series converge, it means the terms have to go to 0. Divergence test tells me what? If those terms don't become close to 0, individual terms don't become close to 0, it means if the limit of the terms, not 0, if those don't become close to 0, then the series diverges. Okay, so divergence test tells me if those individual terms, so this is my sum here, A1 plus A2 plus A3 plus A4 plus etc. If those don't become small, the series will immediately diverge. That's what the divergence test tells us. Okay. And what's important that? What's important that if the limit equal to 0, does this mean the series converge? So if it's not 0, it diverges. Done. However, if it is equal to 0, it means if the term becomes small, can we say immediately the series converge? Yes or no? Back to you.
No.
No. It may converge.
It could converge or diverge.
Or diverge. Okay. Now, yesterday I gave you examples. Okay, and it was just a bunch of sum. So example are, for example, sigma 1 over 2 to the n. That's the example I gave you. This one converged because we knew it converged. It's a geometric series. And so this one converged because geometric. That's the only one we know, basically. And the term go to 0. Okay. Also, we looked at 1 over square root of k. And I did not give you a mathematical explanation. I just added some. But the mathematical explanation for it is, so this is diverge, and the term goes to 0. And I said yesterday, intuitively, they don't go to 0 fast enough. That's really the issue. Okay. Now, why this one diverge? As I said yesterday, I gave you the sum. This one diverge because we can use what we call the integral test. So far, the only thing we know, if the term don't become small, the series diverges. If the series is geometric, we know what happened. But a lot of series will not be geometric for us. Okay, so if those terms become very small, how can we tell? And we're going to see a lot of tests that will help us figure this out. The first one is the integral test. And the integral test tells me if you have a series, sigma ak, f is a function whose value at k is ak, then if this integral converge, this improper integral converge, then my series converge. And the improper integral diverge, the series diverge. That's what we ended up with. And we take 2 examples to elaborate this. Okay, today I will answer your questions from the homework. We will see why this test go, why this test work. And then we are going to study a new type of series. So we studied geometric. We're going to study a new type of series that we're going to call a P-series. Okay. So first, I will answer your question after this review. I do the review because I want the idea to remain clear in your mind before it becomes jumble mumble. So 31 and 11, 31, 13, and 20. All right, let's look at those. Oh, we're still in section 10.4. So we start with number 13, the bottom one on the list. And this is the following. Sigma k equal 2 to infinity of k over the ln of k. Okay, and the question here is the divergence test applicable? If so, use it to decide whether the series converge or not. If it's inconclusive, use it. When it is inconclusive, when the term go to 0, divergence test tells me nothing. We can use the divergence test when the limit of the term is non-zero. If this occurs, then we can immediately say that the series diverges. All right, so in this case, we're going to look, so this is something like that. 2 over ln of 2 plus 3 over ln of 3. That's the series we're looking at. Plus so on and so forth. That's the type of series we're looking at. So the general term is k over ln of k. Now let us watch that here the series started at 2, not at 1. Because if k is equal to 1, I have 1 over ln of 1, ln of 1 is 0, doesn't make sense. So that's why it started at 2, not at 1. All right. So we're going to look what happened to the term as k goes to infinity. Okay. As k goes to infinity, we will have infinity over infinity. That's indeterminate. So we would use the L'Hopital's rule to find the limit. The derivative of k is 1. ln of k is 1 over k. So that's the limit, 1 over k of k as k goes to infinity, which is equal to infinity. It means those terms are huge. Those terms are huge. So I will be really adding bigger to a bigger term to a bigger term. There is no way we're going to get to a finite number. Okay, so it means we can apply. So now the divergence test is applicable by the divergence test.
I have a question.
I'm listening.
So you get 1 over k because you do yes. If you put infinity over infinity in k's place, doesn't 1 over k become 0?
Yeah, If I keep it this way,
Yeah, so
no,
don't
it
that
does,
mean
yeah, sorry, but 1 over k goes to 0. 1 over something very small is what?
oh something very large?
Right.
Oh, okay, okay.
So even if I didn't do this step, I did it by naturally, for me it was k, but even if I didn't do it, I can jump from here to here. All right?
All right.
Okay. So now let's do that's number 13. Let's look at number 20. Number 20. So we have a series which is k equal 1 to infinity of e to the k over 1 plus e to the 2k. And the question here, they want us to use the integral test, right? All right. So the integral test. So we're going to take the function. So this is my ak, my general term is e to the k over 1 plus e to the k. So the function f of x is e to the x over 1 plus e to the x. Okay, so we're going to use the integral test. Now, this function, usually to show it's decreasing, I just want you to graph it. If we graph this function, pick a calculator, this is going to end up to be decreasing, especially in this problem because they tell us use the integral test. So they are assuming it works. So this function here is decreasing. So I'm going to look at the integral from 1 to infinity of f of x. Okay. Now, improper integral, the definition is the limit as t goes to infinity. So now I'm back to the definition of improper integral. I want to evaluate this integral. If this integral converges, I'm fine. If the series converge, diverge, also I'm fine. The series diverge. So the problem really boils down to evaluate this integral. So I'm going to isolate it by itself and evaluate it. Okay. Now, I think we've done something similar to that before. How should I evaluate this integral? Anybody was able to solve this problem? I'll give you one hint. And then I want your ideas. Okay, how should I evaluate this integral?
U substitution,
U substitution. Okay, what's the U?
e to the x.
U is e to the x. So I rewrote it this way because e to the 2x is the same as x squared. So I can see, we can see this. So du is ex dx. And this would become the integral of. This will be swallowed by the du. And this would give me, that's the arctangent u. Since I did not touch my limit, so this is arctangent e to the x. Okay, so that's the integral. So we're back to integral. Now I'm going to go back and find the improper one. So the improper integral is, so integral from 1 to infinity of ex over 1 plus e to 2x dx will become the limit as t goes to infinity of arc tangent ex between 1 and t. All right, so this would give me the following limit. Arc tangent e to the t minus arc tangent e to the power 1. All right, and now this is equal to what? Remember, the arctangent is the angle. It's the angle whose tangent is e to the t. Now, when t goes to infinity, e to the t goes to infinity. The angle whose tangent goes to infinity is pi over 4. I meant pi over 2. Pi over 2 is the angle whose tangent goes to infinity. So it's going to give me pi over 2 minus arctangent E. I have no clue what arctangent E is. I have to plug it in. But this is a finite number. That's the only thing I really actually care about. It means it's not infinite. So the integral converges. The series will converge. By the integral test, sorry, because you're going to see a lot of tests. So I have to write which test I am using. By the integral test, series could integral converge, the series will converge. The integral test usually is not hard, but it's just a matter of evaluating the integral. Converges. Okay. Now I'll look quick at your other problem, and then I will explain where this magical test is coming from.
Can I ask a question about that real quick?
You can ask any question.
All right. So can you explain real quick how you got arctangent of e to the t to be pi over 2?
Yeah. What's the arctangent?
Inverse tangent.
What does it mean?
Adjacent over opposite.
No. What's arctangent? What's arctangent of, let us say, of 1? What's arctangent of 1? Anybody can pitch in? What's the arctangent? What's the definition of it?
Pi over 4.
Why? What's the definition? You're right, pi over 4.
It's the angle opposite. No, it's
I don't want you to use. I don't want you to use opposite. I don't want you to use whatever adjacent. I don't want you to use those two words.
You go from the number to the angle. That's what.
Right, it's the angle whose tangent, exactly, whose tangent is 1. In other words, arc tangent 1 is the angle theta, whose such that tangent theta is equal to 1. That's the arctangent. It's the angle theta such that tangent theta is equal to 1. Which angle is tangent is 1 pi over 4. So arc tangent 1 is pi over 4. So that's really what the arctangent. It's the angle theta whose tangent is 1. Now, what I'm interested in is, suppose what's the arctangent of t? Let's use t when t goes to infinity. Or let me use another. Sorry. The last thing I wanted is this. So my question to you is the following. This is the graph of arctangent, of tangent. So that's t, and that's the tangent function. Or let's see, call it x. How does the graph of tangent looks like? This is pi over 2. The graph of tangent goes like that. Okay. What's the arctangent? Arctangent 1 means the tangent is 1. What's the angle? That's really what's the angle. What's arctangent 2? The angle is 1. What is the angle? That's really what's arctangent 2. So the arctangent are the angles whose tangent is this number. So now the question is, what's the limit of arctangent e to the t when t goes to infinity? Okay. It means, what is the angle whose tangent goes to infinity? When t goes to infinity, goes to infinity. The question is, what is the angle whose tangent goes to infinity? According to the graph, what's the angle whose tangent goes to infinity? So I'm looking for the angle such that its tangent is very large. The angle whose tangent is very large is the angle pi over 2. So here I'm asking myself, what is the angle whose tangent is very large. It is pi over 2. So I'm going backward from here to here. So what's the angle? If the tangent is very large, what's the angle? Let's give me that a high tangent. It's the pi over 2 angle. Because we're going always backward. Does it make any sense?
Yeah, that makes sense.
A little
I
bit?
understand that. Thank you.
So let's look at the last problem, and I have a lot for today. So I'll look at the last problem, and this should not be hard. 1 over k minus 2 to the power 4. Okay. Again, we're gonna use, so here they tell us, what's the question here? Use the divergence or the integral test, all right? So divergence or the integral test. Let's see if the divergence tells me anything. So AK is 1 over k minus 2. So we're gonna check the divergence test. So now as k goes to infinity, what's the limit of AK? Back to you. What's the limit of AK as AK goes to infinity? What's wrong with you?
It's approaching 0.
Yeah, it's the limit of 1 over k minus 2 to the power 4. This is equal to 0. So can I use the divergence test? Yes or no?
No.
Can I say that the series converge? Yes
No.
or no? No. So the divergence test is absolutely inconclusive. Tells me nothing. Tells me nothing about the series. So I don't know whether the series converge. I don't know whether it diverge. I don't know what's it going to do. All right, so I have to use another way to do it. So we're going to use the integral test because that's for now the only thing we know. We use the integral test. All right, so actually if we write up this term, it's not a hard series to write up its term. If k equal to 3, again, they cannot start at 2 because if k equal to 2, I will have 2 minus 2, 0. So they started at 3. So if k equal to 3, I'm going to have 1 over 3 minus 2, 1, plus k equal to 4. I will have 2 to the power 4, 3 to the power 4, 4 to the power 4, and so on and so forth. So use the integral test. And now when I'm going to use the integral test, I'm going to look at the following integral. I will not start at x equal to 1. I'm going to start exactly what they are starting. So we're going to start from 3 to infinity of 1 over x minus 2 squared. Sorry, to the power 4 dx. Okay. And then, sorry, here, my AK is 1 over k minus 2 to the power 4. It means my function is 1 over x minus 2 to the power 4. Now, definitely, this is a decreasing function because when x increase, the denominator increase, 1 over the denominator basically will decrease. And graphically, that's this function has issue at 2 because x equal to 2, we have an asymptote, but we are interested from 3 and above. That's why we're moving to 3. We're not starting at 2. And from 3 and above is going to look this positive and will definitely look a decreasing function. Okay, so 2 give me a problem, but the question is totally avoiding 2. So I have to look from 3 to infinity because I need to avoid 2, totally, absolutely. So this is equal to the limit. Now the problem is becoming easier of the integral from 3 to t of 1 over x minus 2 to the power 4 dx. Now the question is to evaluate this integral. So I will do the indefinite one because I have x minus 2. A simple substitution is in order. The du is the dx. So this would give me the integral of u to the minus 4 du, because the du equal dx, which will give me 1 over minus 4 plus 3 minus a third u to the power 3. It means minus 1 over 3 times x minus 2 to the power 3. So as you realize, it's a matter of integral. So finally, the improper integral will be the limit as t goes to infinity of this one. Between 3 and t. So that's the lower limit is 3, the upper limit is t. So this would give me equal to the limit as t goes to infinity of, okay, 1 over minus 3 times t minus 2 to the power 3 minus minus, because indefinite, the fundamental theorem, if tx equal to 3, 3 minus 2, it's a 1, I will get a third. That's equal to what? Now, when t goes to infinity, t minus 2 goes to infinity. So 1 over it is going to become very small. So I'll end up with 1/3. So it means that the integral converges. So by the integral test, the series converge. Okay, and that's what this one will do. Okay. All right. So now what I want to do is, I was hoping to show you why the integral test work. So I will show you a little bit quickly why the integral test work, just to show you that things don't come out of thin air. And then I hope I will have time to do the last idea I was planning to do today. So why the integral test go? I wanted to listen. The proof is in the book, so you don't really have to write it, but I want you to listen a little bit. And I'm going to do it via an example, not the whole thing, because the whole idea is just verbatim like the example. So let's see why the integral test works. Why? I'm going to show you the following example. Let us see. I'm going to take the following series. Sigma 1 over k squared. And the question is, why the integral test will make this series converges, all right? So the integral test takes the series and compare it to the following integral. So we take equal, so ak here, sorry, is 1 over k squared. And so my f of x is 1 over x squared. And let me evaluate integral from 1 over x squared before I explain why the test will work. This is very easy. That's the limit of minus 1 over x between 1 and t equal to 1. So this integral converges. Now, what's the relationship between this integral and between the series? And that's really what I'm going to try to explain to you right now. All right. I'm going to draw a graph right here. Okay. And I'm going to sketch the function 1 over x squared. Okay, so this is the graph of 1 over x squared. And this is x. And my idea is that why, if this integral converge, the idea is that why, if this integral converge, then this sum will converge as well. What's really going on mathematically? Now let's remember, what does it mean for a series to converge? Series converge if the partial sums themselves converge. So I really have to look at the partial sums to define everything. Let's see what the partial sums are. The partial sums are S1 is 1. It's sigma 1 over k squared. So I will write the series here in front of us. So my series is sigma O 1 over k square, k equal 1 to infinity. Okay, S1 is 1. S2 is 1 plus 1 over 2 square. And these are what I'm interested in. S3 is 1 plus 1 over 2 square plus 1 over 2 cube, and so on and so forth, right? And Sn in general is 1 plus 1 over 2 square plus etc. up to 1 over 2 to the n. So that's the general term of Sn. Okay, now I want to go back to the graph and start finding this relationship between the sum and the integral. So I'm going to write this as a 1, a 2, 3, 4, etc., etc., etc. I mean, and this is, let us call it n. I'm going to call this n plus 1. Okay. And I'm going to look at the following rectangle. So I'm going to take this rectangle. Okay. The following rectangle. This is my first rectangle, my second rectangle, my third rectangle, and this is my, let us say, nth rectangle. Now, before I take my rectangle, what's the coordinate of this point? This is the graph of 1 over x squared. Means this point here is 2, and this is 1 over 2 squared. Means this height from here to here, this is 1 over 2 squared. And this height from here to here is 1 over 3 squared, 1 over 4 squared. All right. Now I'm going to start the comparison. S1 is 1. All right, I'm going to keep S1 is 1, nothing to do about it. Now S2 is 1 plus 1 over 2 squared. I'm going to look at this term. 1 I'm not going to touch because I can't. 1 over 2 squared. In the picture, what is 1 over 2 squared? You look at the picture very carefully. 1 over 2 squared is the area of this rectangle. Agree with me? It's this area, because from here to here I have a 1. From here to here, 1 over 2 squared, so that's the area of this rectangle. So 1 over 2 squared is going to be, and this rectangle, I'm going to compare it to the area of the graph, under the graph, from 1 to 2. So from the picture, I say that this is less than, this piece is less than the area, the red area, which is the integral from 1 to 2 of the function f of x dx. So I'm doing it slowly to understand. Okay. So what I did so far is 1 over 2 square is the area of this rectangle. It's less basically than the area under the curve from 1 to 2. Now, what is F3? Equal to, I'm going to repeat the same process. I'm not going to touch 1 because the problem will not work. So I'm going to look at those two pieces here. Those two pieces. All right. 1 over 2 square is the area of this rectangle. 1 over 3 square is the area of that rectangle. So the area of this plus the area of that now is going to be less than the area under the curve from 1 to 3. So this is going to be less than integral from 1 to 3 of the function, which is 1 over x squared. I keep idea going. I keep doing the same thing. So, but then I say, what is Sn? Sn is what? It's 1, I'm not going to touch, and it's this piece that I'm going to work with. Plus, now, 1 over 2 square is actually the area of this piece. 1 over 2 square over 3 square is the area of this rectangle. 1 over 4 square is the area of this rectangle. 1 over n squared, so probably I should put n minus 1 here and n here. I don't know why I did that. From here, if this is n, from here to here, this is 1 over n squared. So that's this area of this rectangle right here. So 1 over 2 square is this area And then, so this is, I'm adding those areas. I'm adding those areas. I'm adding those areas because the width is 1. So it's the height times width. I'm adding those areas and etc. But this is going to be less than the area under this whole curve. So this is going to be less than the integral from 1 to n of the function. Okay. So the sum Sn is going to be less than 1 plus the integral from 1 to n of f of x dx. So now, what do we know? So it means that if I take 1 plus 1 over 2 squared plus 1 over, oh, no, it's not 2 to the n, sorry. You guys have to correct me. It's 1 over x squared, so this should be 1 over 3 squared. It's 3 squared here. And this is n squared. My apology. Okay, 1 over n squared. So this is going to get me to the following. If I take 1 plus 1 over 2 squared plus 1 over 3 squared plus etc. 1 over n squared, this is less than 1 plus the integral from 1 to n of the function, which is 1 over x squared dx. So that's Sn. Okay, that's the sum. But, however, so it means that this sum, I can make it less than the following. One plus the integral from 1 to n is definitely less than the integral from 1 to infinity of 1 over x squared. Because the integral from 1 to infinity, it means basically I'm taking the graph all the way up to here. 1 to infinity, it means I'm taking this whole area. But this one converges, and this is going to be equal to 1. It means my sum, Sn, no matter what n is, going to be less than 1. This one converges. That's really where my idea is using the integral. This one converges. It means the sum is going to be less than 1 plus 1. It means this sum is going to be less than 2. So all my partial sums are going to be less than 2. So it means if I add 1 plus 1 over 2 squared plus 1 over 100 squared, I get less than 2. If I add the first 1,000 terms, I get less than 2. The first 1,000,000 terms, I get less than 2. So the sum are always, those partial sums, they keep basically increase, but they can never exceed the 2. They're always less than 2. So this tells me that the limit cannot blow up to infinity. So the limit basically exists. It's less than 2. It's not equal to 2 because as you realize, it's bounded above by the graph and that is by the area under the graph. So it's less than 2, but it cannot blow up to infinity because it's always bounded by 2. So that's the reason we can compare the integral to that. So if this one converges, the sum being less than it will also converge. Now the question is that if this one goes to infinity, everything falls apart. If this integral is infinity, it means the sum, I cannot bound them above by something. So the sum can diverge. And that is another, we need another geometrical idea to show why it will diverge. So the last piece is why, if the integral diverges, then the sum diverges. Okay, so I will show you this, so I will have a peace of mind, and the last idea I want to talk about has to wait for tomorrow. So now my question is the following. We're going to look at the series. Sigma 1 over n. It means 1, so 1 over k. 1 plus a half plus a third, plus a fourth, and so on and so forth. And my question is, I'm going to take the integral from 1 to infinity of 1 over x dx. Okay. And I'm going to evaluate this, and then we're going to talk why, and let's see what if this converges or diverges first. So that's the limit of ln of x between 1 and t. So it means that's the limit. As t goes to infinity, ln of t minus ln of 1, which is 0. So it's equal to infinity. So this integral from 1 to infinity diverges. It means the integral test tells me that sigma 1 over k, it means those terms, 1 plus a half, plus a third, plus a fourth, even though they become small, but when we add them, the sum is going to blow up. That's really what's happening here. And this series is an important series, and it's called the Harmonic Series. Okay, so this series, what we will show now, that even the term becomes small, it will diverge. And let us see how the integral come into the picture. So again, we're gonna use the same technique. I'm gonna graph the function 1 over x. This is 1 over x. 1 over x. And this is the graph. I'm gonna compare the series to the integral, so we understand where it's coming from. So I'm gonna kind of imitate the previous problem, but there will be a twist. In the previous problem, I cannot imitate it verbatim, because in the previous problem, what I had is the Sn less than the integral. But if the integral goes to infinity and Sn less than it, I cannot say Sn goes to infinity. So we're gonna make a slightly different argument. All right, so again, to understand a sum, we have to go to its partial sum. So S1 is 1 here. S2 is 1 plus a half. S3 is 1 plus a half plus a third, etc. Sn is 1 plus a half plus a third plus etc. 1 over n. That's really my partial sums. Now I'm going to compare them to the integral. And let's see how we're going to do that. I'm going to take, if you want to think about it as left triangle instead of right before. So this is my 2. This point is 1, 1, because that's the point on the graph. This point here is 1, 1 half, because that's the function 1 over x. This point right here is going to be 1, 1/3, because 1 over x, and so on and so forth. So I'm going to take the following rectangle. Okay, the following rectangle. And then I'm going to start analyzing. S1 is 1. If I look at the first rectangle, well, let me not worry about S1. Let me take S2. Let's look at what's at S2. It's 1 plus a half. I'm going to visualize this. If I take my first rectangle, what's the area of my first rectangle? From here to here, I have 1. So the area is 1. Let me take this rectangle. The area of this rectangle is 1/2. This is 1/2. And from here to here, it's 1. So it's 1 times a half, 1 times a half. So S2 is the area here plus the area of this rectangle. But the way the picture is, this is larger than the area under the graph, because the area under the graph, this is my graph down here. This is my graph. The area under the graph sits below. That's the area under the graph. So the sum of the area this rectangle plus this rectangle is going to be larger than the area under the graph. It means larger than the integral. From 1 to 3, we're going to go up to 3 in this case, of the function f of x dx. Now, what is f3? f3 is going to be the following. The same idea. Look at this rectangle. From here to here, I have 1/3. So the area, and this is 1. So 1/3 times 1 will give me the area of this rectangle. So 1 plus a half plus a third give me the sum of the area of those rectangles. Now, in terms of the picture, if I look at the graph up to 4, right here, up to 4, then the sum of the area of this rectangle is larger than the integral from 1 to 4 of f of x dx. So the sum is larger than the integral. Now I keep going verbatim the same approach because I actually want what happened to the in general. So suppose this is n, and this is my n plus 1, because as we realize, f3 is integral from 1 to 4. So I'm gonna take this right triangle, this rectangle, and now basically I'm repeating myself here. So this is going to be bigger than the following. Integral from 1 to n plus 1 of f of x dx. So the sum now, every sum, so if I add the first n terms, it's going to be larger than that. But now let's see what's happening for this integral in this particular case, because I need to finish. So I will have Sn, any sum, it's 1 plus a half plus 1 over n. It's larger, and that's important. It's bigger than the integral from 1 to n plus 1 of 1 over x dx. But then we know what happened to this integral when n becomes large. So when n goes to infinity, when n becomes large, what's going to happen? This integral here is going to go to infinity because this integral diverges. It means those sums will go to infinity. Okay, so every sum is larger than the integral. When n becomes large, this integral is going to blow up. It means the sum themselves are going to blow up. That's really what's happening here. So when n goes to infinity, since this integral goes to infinity, because the integral diverges, it's the when the upper bound goes to infinity, the infinity diverges. It means the sum Sn itself will have to go to infinity because the sum is larger than that. End of the problem. Okay, and that's really why the integral test works. So this is one of the few proofs I will show you, because later on the proofs become a little bit harder. So we just understand things, understand how to do them, but that's how the integral test goes. So if the integral diverge, the partial sums are going to be bigger than the integral, causing the partial sums to diverge. If the integral converge, I can create the scenario to make the partial sum less than it, and then they will converge. Right? Okay, so that's it for today. You guys do your homework. You may get stuck on the last one I assigned. So if you get stuck on it, don't worry about it. So everything else should be basically a bunch of integral tests. All right, bye-bye.
Have a good day.
You too, bye-bye.